Good afternoon, everybody. My name is Sostaric. I'm here today because I'm passionate about the Martian. I'm passionate about landing humans on Mars, and frankly, I've volunteered before I had any idea what I was getting into. But seriously, though, I'm really glad to be able to join you and talk about Mars. It's fun stuff, and it's the future. So let's talk a little bit about Mars. When I first came to NASA, I always wanted to, when I was growing up, I thought Mars was great. I wanted to go to Mars, right? I want to send people to Mars. When I first came to NASA, I got an opportunity to work as a co-op. And at the time, we were developing entry systems for humans to Mars. And the plan is 25 years, humans to Mars. Well, about 20 years later, I'm still here. We're working entry systems for humans to Mars. The plan is 25 years, humans to Mars, right? Okay, so we want to get that closer, right? We want to bring that 25-year number down. We want to bring it, get it down to funding cycles or something like that. So close that gap, if you will. And so I'd like to tell you today about some of the things that I'm doing personally to try to make a difference in closing that gap. First, let's talk about The Martian. So, The Martian in the book, and for those of you who haven't read it, don't worry, I'm not going to spoil it. This happens in the first 5 pages. But in the book, the crew lands on Mars in the Mars Descent Vehicle, or the MDV, and it's described as, in one sentence, a can with some light thrusters and some parachutes attached. So I took the liberty of drawing up some concept art for the concept, and I hope Andy Weir doesn't mind too much. Maybe he can call me for his next book or something. Seriously though, so let's talk about Mars for real. Mars is different than Earth, as we know. The atmosphere is different. It's mostly CO2, but what's really important for, as far as we're concerned with Mars landing, is that the density is much less. It's about 1% of the density of Earth. So what that means, think about that, the density at the surface of Mars is about the same as 100,000 feet on Earth, which is over 3 times the height of Mount Everest. There's just not a lot of air density to work, or sorry, not air, Mars, not density to work with. Well, okay, so most of you probably know, but why do we care? We use drag to slow down the spacecraft in Mars. And that drag force is proportional to the density. So if the density goes down 100 times, the drag force goes down 100 times. So it's a challenge just to slow something down at Mars. At the same time, there's still enough density to create significant heating. So we have the same kind of thermal protection system concerns that you would have for an Earth vehicle. And we use ablative TPS to keep the payloads and the astronauts safe, of course. Get a feel for the density difference. There's a constructed example here. So imagine a skydiver at Earth, no parachute. So they're going to have a bad day probably when they hit the ground, but they'd only hit the ground at 120 miles per hour. At Mars, it's a Mach 1.5. So not only would they hit the ground really hard, but you wouldn't even hear them scream until after they hit the thump. So, it's a big challenge. Lest you get worried about the rest of the presentation, this is not the proposed system for landing humans on Mars. Okay, I've convinced you probably that it's a challenge, but we know how to land on Mars, right? We've done it 7 times. Most recently being the Curiosity rover, the Mars Science Laboratory, MSL. So while we're on the chart, I have you note also that they're at relatively low elevation landing sites. None of these are in the Southern Highlands. Okay. What have we landed there? Things that some of them look like this. Mars Pathfinder is the small rover you see. The medium-sized golf cart type of rovers are Spirit and Opportunity. And Curiosity is the large one there. So that's about how big Curiosity is next to some people. So that gives you a feel. The entry vehicles that we put those rovers in are depicted here on the plot. And so you can kind of see roughly what the size is. And they've used the same basic technologies that were first developed for Viking program. And that's the 70-degree sphere cone aeroshell shape. and the Mars Supersonic Disc Gap Band Parachute. Those technologies are not the ones that will scale well for the kinds of human missions we need to send to Mars. Let me tell you a bit about why. Imagine the Curiosity rover as a unit, and the closest thing I could find through an internet search was a smart car. And so one smart car is Curiosity. Well, for our human missions, they're much larger, right? We're talking about 20 to 40 times the payload mass that's required. So that's 20 to 40 smart cars each time we land. So that gives you a feel for the difference in size. Also, to give you a feel, imagine now this is roughly to scale. So you've got a 4.7 meter Mars Science Laboratory, MSL there, and a 20 to 30 meter long entry vehicle for humans. So they're much, much bigger. At this point, you're probably going, well, wait a minute, why do I want to land something big? Why don't I just land a bunch of small stuff, right, instead? And I don't have time to kind of go through all the different reasons, but I wanted to at least address the landing accuracy part of that. Landing accuracy for Mars has steadily improved. As you can see, Viking had a fairly large landing ellipse, and it's gotten better, smaller. Folks worked hard on this, getting it down to the size of Curiosity, but it's still here 12 by 4 miles, right? So imagine instead of sending all the smart cars all at once, we're going to send 20 to 40 smart cars. In fact, that's not the total mass we need for the mission, but you get the picture. And then we'll send people to go and collect all the supplies and gather them up and bring them back. Okay, so imagine that's a mission scenario. Well, when we send the crew, they're going to need all the things to go get all those supplies, right? They're going to need life support and a HAB and a really capable rover to go over such a large area. Not to mention the other concern with, some of those supplies might land on top of each other. So the system that's going to have to send that would have to go at the same time as the crew to be safe is going to be fairly large because of all the large components that need to come with it. And so the smart folks who work the EDL architecture trades have figured out that the sweet spot for the total number of landings is 2 to 4, and that's what drives the large masses I've been talking to you about. NASA is not sitting idle. We're hard at work on some different technologies that help address each of the things I've talked to you about. The first one is low-density supersonic decelerator. So if you've heard of the flying saucer test, that's this. This is about incremental capability improvements to current robotic mission capabilities. So instead of landing 1 metric ton on Mars, we'll land 2 metric tons on Mars, or we'll go land at the Southern Highlands. ALHAT, near and dear to my heart, I worked on it for 6 years, great project. It's the Autonomous Landing and Hazard Avoidance Technology project. ALHAT's addressing the landing accuracy that I talked about, and it's about kind of 2 things. The other aspect is knowing what's at the landing area, knowing the landing site. Are there hazards? Are there assets that are already there? And then going and landing and avoiding those. So ALHAT's working on that. And you probably know it was flown on Morpheus as well. So made great progress on ALHAT. For entry, hypersonic entry, there's basically 2 categories that NASA's investigating, and that's these, one is the large blunt body shapes, so the deployables and inflatables. And the basic idea here is, and it's different from Doug's type of application, but it may relate a bit. But the idea here is you'd package the spacecraft in the launch vehicle in the shroud, and then on the way to Mars, inflate or deploy something that would allow you to get a lot more drag area than you could otherwise stuff into a launch shroud. The last one is also near and dear to me, is the mid-lift-to-drag aeroshell technology work, and I'm personally working on this. So here you see 2 of the concepts we got. The idea here is to get extra lift-to-drag ratio to do some useful things for the mission as compared to, this is why we call it mid, is because this is compared to the low LRVD blunt bodies or capsules, but the mid-LRVD is not as high LRVD as, say, something like a winged vehicle, like the shuttle. Shuttle is about a 1.0 LRVD. Mid-LRVD is about 0.5 to 0.6. So why do we want the LRVD? There's 3 things about the LRVD that was really helpful for us. One is that it will help better manage the entry loads, so the entry Gs, better cross-range capability, and the third thing is landing accuracy. More LRVD leads to better landing accuracy. What might it look like for an actual human Mars EDL? So this is a concept. There are many concepts under investigation, but I'd like to just talk you through one so you get a sense of what EDL looks like, entry, descent, landing looks like. So you'd fly the hypersonic entry with the vehicle, and as it gets closer to the ground, this is where things get interesting. This concept shows a transition in which the aeroshell splits and a lander emerges, and the lander would do a power descent burn beginning from a supersonic condition and come down and land the payload or crew. All of the concepts are under investigation. Almost all the concepts under investigation have an initiation point for this powered burn, a supersonic Mach number. There are a few that can get it to subsonic, but we're talking really large, probably infeasible types of drag areas. So keep that in mind. Hopefully I've given you a feel for the challenge of Mars, but we didn't talk about how to close the gap. And so that's what I'd like to talk about next. So before we test anything or fly it at Mars or use it, we would develop it and test it here at Earth. And I've been involved in doing some of that. So took the mid-LRVD idea that I've described to you and joined forces with the Mariah Capsule project to do subsystem development and testing for that would be applicable to an Earth demo version of this Mars aeroshell shape. So what's the Mariah Capsule, you're wondering, right? I got a picture for you. So the Mariah Capsule idea was to build a small spacecraft, a 30-inch, 150-pound spacecraft, take it to the space station, deploy it out the GEM airlock, and have it return small payloads, small samples. So this is what it looks like. I would just like to show you some pictures about it and talk about the concept that I'm really excited about. So we've done a bunch of testing. Here we're getting ready for a test. This picture cracks me up, so I included it. Got the data on that one, good day. Recovered that one as well. Some chute testing and high altitude balloon tests, which takes us to the TRV, the Terrestrial Return Vehicle, which is the Earth demonstration version of our mid-LRVD shape. So I'm really excited about the work that I'm getting to do on this. It's fantastic. This will be a 4-foot version of that 20 to 30 meter long aeroshell that I described to you. It will fly late next year, so we're developing it right now. It would go up onto the space station, deploy out the GEM airlock, as I mentioned, like the Mariah capsule, but passive deploy, does a separation passively, gets a safe distance away, does a deorbit burn, enters and lands on a parafoil for an accurate landing. So super exciting project. We're working on it right now, and we're really excited about it. So I'd like to close with a personal story, if I can get the slide to change. This picture is near and dear to me. Of all the testing we've done and development testing, this one is just my favorite. It's from our very first test. So we're high altitude balloon test. I was doing some prototype work out at the sandbox here to develop this system, and then working with a couple of the co-ops who are willing to do this crazy thing with me. And we'd done some testing here. I took it home, painted it this ugly orange color. It was not my choice. It was for recovery purposes. In my garage at home. stuck it in my freezer, did a cold soak test, and my wife was telling people, there's a spaceship in my freezer. It wasn't a spaceship yet, but it became one. This picture's evidence, right? But the best thing about it, I got to involve my then 3-year-old son, and so we took the system in the backyard, and we were very safe, but we did parachute deployment testing. And so I had him, he and I did a countdown from 10, and he hit the button, and the parachute would pop out, and at first it only went this far, it wasn't very impressive, but with some design tweaks and changes, it got the thing to work pretty well, and it worked great in flight. And I got to bring this picture home and show my son and say, look what you helped make happen. So it was just a great experience. So I hope that someday we can say the same kinds of things about being part of landing humans on Mars someday. Thanks for your time.